Hello again and welcome to our lesson video notes over 8.2 Pythagorean Theorem and its converse. And so we're going to jump right into chapter 8 with this first lesson. We're actually skipping 8.1 and going straight into 8.2. And we'll talk about Pythagorean Theorem, and a lot of this was covered in class already. We already talked a little bit about these Pythagorean Theorem and those Pythagorean inequalities, but we're just going to review some things to make sure you have good information to move on. So let's get started with our short video. Alright, so in the past we've used Pythagorean theorem and we developed the distance formula in the coordinate plane. We're also going to take a look at the implications that might have with three-dimensional graphing, and we'll take a look at that later on in the video. And so we're going to use the Pythagorean theorem, and we're going to use the converse of the Pythagorean theorem to do some calculations today. So just a quick little review of Pythagorean theorem. In right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. In short, a squared plus b squared equals c squared. And so then that leads us to what we call Pythagorean triples. Pythagorean triples are whole number values that work in the Pythagorean theorem, where c is always the largest value, which would end up being the hypotenuse of a right triangle. And so you've got some here that are given to you, and then I've given you a whole lot more here, so you may want to take time at some point to write these down. 3, 4, 5, and then 6, 8, 10. 6, 8, 10 is just a variation of 3, 4, 5. It's just the second multiple of those. Then we have 5, 12, 13, and then again it's different variations. But we also have 8, 15, 17, 7, 24, 25, and then the list could just keep going on and on and on. There's many more Pythagorean triples that we've encountered where we have whole number values that fit a squared plus b squared equals c squared. Alright, so we took a look about the Pythagorean theorem converse. And the Pythagorean theorem converse says if a squared plus b squared does equal c squared, then it is a right triangle. But if a squared plus b squared is less than c squared, it would be an obtuse triangle, like we learned from our exploration earlier. Whereas if a squared plus b squared is greater than c squared, it is an acute triangle. So we can use these two inequalities to figure out if a triangle is either obtuse or acute, and then we can use the Pythagorean theorem itself, the equation, to see if it is a right triangle. Okay? Now remember, to be a triangle, the sum of the two shorter sides must be greater than the longest side. And so here's what we check. We just check a plus b to make sure it's greater than c, where c is the largest value. Okay, so we check that to figure out if it's a triangle, yes or no. Then we can use these where we square those values and add them to see what kind of triangle it is. So we're going to determine whether the following values would form triangles. If yes, we need to write obtuse, acute, or right. Okay, so here's what we have, 5, 6, and 8. So we're going to check the smaller two. 5 plus 6, is that greater than 8? Well, 5 plus 6 is 11, which is greater than 8, so yes. Okay, and then we can evaluate 5 squared plus 6 squared. Well, that's 25 plus 36, and 8 squared is 64. 25 and 36 makes 61. 61 is less than, so a squared plus b squared is less than 8 squared, or c squared. So since a squared plus b squared is less than c squared, this is an obtuse triangle. Okay, let's try one more example. 15, 13, and 30. Let's try and add these together and figure out if it forms a triangle. Okay, 15 plus 13, that is 28. 28 is less than 30, or not greater than. Since it's not greater than 30, this is not a triangle, so it doesn't need to be classified because it's not a triangle. Alright, so using these as your guide, why don't you guys go ahead and try and do these next few on your own. And some of you might already have these done, you might have done these in class, but go ahead and try and check first to see if it's a triangle. Answer yes or no. If it is a triangle, if your answer is yes, then classify it as obtuse, acute, or right based on your Pythagorean inequality or the equation a squared plus b squared equals c squared for right triangles. Alright, if you need more time, pause the video. Otherwise, these are the answers we should get. Okay, for number 1 here, 8 plus 10 is greater than 15. 18 is greater than 15, so yes, it's a triangle. And 8 and 10 are the shorter sides, so we say 8 squared plus 10 squared, which is 164. That is less than 15 squared, 225, so that's an obtuse triangle. Remember, if a squared plus b squared is less than c squared, it's obtuse. Okay, 7, 24, and 25. 7 and 24 are actually the smaller two, so we add those and we get 31, which is greater than 25. So yes, it's a triangle. And if we plug those in, we actually get 625 on both sides, so it means it's a right triangle. Okay, 3 is a triangle, and it's acute. 4 is not a triangle. 8 and 3 are the smaller two, so we add those and we get 11. 11 is not greater than 12, it's less than 12. So no, it's not a triangle. And then lastly, number 5, it is a triangle. 11 plus 12 is more than 18. And so when we add those together, we get 276 for a squared plus b squared. That is less than c squared, 324. So again, we have an obtuse triangle. Alright, now that leads us to talking about three-dimensional graphing. When you turn the page, you'll see we've got three-dimensional graphing. Graphing in 3D means there's an x, a y, and a z axis. There are three axes. So I've given you some examples here, and I'm getting ready to show you a different example with some real-time movement that allows you to see that a little bit better. But we will use the x and y axis kind of just like normal. It's like we've taken our xy coordinate plane and just laid it down, and then we put z down through that axis. And so we have all these potential ways of representing our three-dimensional axis. And we have a 3D plane with an x, a y, and a z axis drawn this way, where you can see the negatives and positives of both, or sometimes we just focus on positives and we kind of turned it a little bit. And then we have this, again, x-axis, y-axis, and z-axis, and there's some ways we can see that. Okay, here's a better look at what the 3D coordinate plane might look like. Okay, here you'll see an app that I've got on my iPad here that shows you a three-dimensional graph, and it may not look like that. It may just look like you have an x and a y axis. Actually, this is axis z, and there's a y, what looks like right in the middle. And if I touch and I drag, you can kind of see three-dimensionally now that is your y-axis running this direction. And the more I move it around, the more I see how that works in three-dimensional time. It puts that nice cube around it so I can examine my graph from any angle. And we're not going to do a lot of this kind of graphing. Kind of snap it back to where it's easier to see. We're not going to do a lot of this kind of graphing with this kind of technology, but hopefully later we'll be able to explore that some. But you can kind of see what a 2D representation might look like. Okay, might look a little bit like this. All right, and so I've drawn in the scale there. And so we have our x coordinates, positive and negative, our y coordinates, positive going back and away, and negative coming up closer towards us, and our z coordinates, up is positive, down is negative. All right, so let's take a look at some of those kinds of examples. So we can use our Pythagorean theorem to get a distance formula in the coordinate plane where a, b, and c refer to those multi-directional values. Or if we write it out this way, x2 minus x1 squared plus y2 minus y1 squared, that looks like your distance formula that you're used to seeing. And then all we have to do is add in the difference of the z coordinates now for three-dimensional graphing. So all we have to do to find our lengths here, and I'm going to go ahead and try and plot these coordinates for you, and I'm going to use a ruler to help me demonstrate that. Okay, I'm actually going to plot the points on the graph so you can kind of see what that is, and they always go in order x, y, z, x, y, z, x, y, z. Okay, so this first coordinate for A has a x-coordinate of 3, so I'm going to go to my x-axis, which in this case is running front to back. Now sometimes these get turned to where this is x moving left to right, but for this case x is moving out towards the middle. Okay, so x has the x value of 3, so I count out here 1, 2, 3 places. Alright, so I'm going to just make a very faint line through that x value. All right. Then my y-coordinate is 5, so my y-axis is the one moving left to right, and so the right side is positive, so we're going to count 1, 2, 3, 4, 5. Okay, and I'm going to move parallel to that x-axis by marking this. Okay, now this is all in the 0 plane for the z-coordinate, so I have to move up 2, 1, 2 here, but now that means I'm going to have to move that same distance up 1, 2 in this direction. So here's how we're going to do that. All right, I'm going to draw the kind of quick little imaginary parallelogram. And so this would be point A. Imagine that being out in 3D space right there. Okay, we've gone forward 3 in the x value, over 5 in the y value, and then up 2 for the z value. And then b is at -1 for the x, and so I go back here to -1. And then -3 for the y value. It's back this direction. 1, 2, 3. And you get to where you kind of can do this free-handed a little bit. And then +4 for z, so we're going to go up here. Okay, and that would be point B. And if I were to connect A and B, it'd be very difficult to try and count or measure that distance. And so what we have to do is use our coordinate plane. Instead of using the coordinate plane, we want to try and use our formula here. So we're going to use that distance formula and just plug in the coordinates. We're going to subtract the x's first. So I'm just going to pick an order and stick with it. I'm going to go from A to B. So I'm going to do 3 minus -1, or 3 plus 1 squared. Then I'm going to use the same order for the y's. I'm going to do 5 minus -3, or 5 plus 3 squared for the y's. And for the z's, I'm going to do 2 minus 4 and square that. And then I just simplify. 3 plus 1 is 4. 5 plus 3 is 8. And 2 minus 4 is -2. And then I have to square those. 4 squared is 16. 8 squared is 64. And -2 squared is 4. So when I add these all together, 16 plus 64 plus 4, I get the square root of 84. And now we can write that one of two ways. I can simplify the radical, or I can round that. So the radical simplified gives me 2 root 21, because 84 can be divided by 4. That's the largest perfect square factor of 84. And then that is approximately 9.17 if I round to the nearest hundredth. So either way of writing that answer is acceptable. Okay. Now, without having to graph the segment RS on the coordinate plane, we're not going to take a bunch of time in the video to do that, but I do want you to use your coordinate points in 3D distance formula, like we did here, to find the length of RS, just using these coordinates here. Okay, so go ahead and set that up and try and find that distance and write it as a simplified radical and round it to the nearest hundredth, please. Alright, if you need more time, go ahead and pause the video. Otherwise, this is what we should get. Alright, we do get the square root of 53, which cannot be reduced into a simplest radical form. So the simplest radical form is just the square root of 53, which is approximately 7.28. Alright, we'll do a lot more work with this, especially the simplifying radicals part of this, as we take a look at the rest of this lesson in class. So hopefully you understand things a little bit better about Pythagorean theorem, and we will do some more work in class.